Welcome everyone, my name is Pablo Valdez. I am from the University of Texas at Dallas. Today I will be discussing my summer research project on evaluating prompt engineering strategies for large language model based vulnerability patching. This project is a comparative study of few-shot and chain-of-thought approaches. Software vulnerabilities continue to represent a critical threat to system security, yet automated vulnerability patching remains significantly less studied than detection. While recent work has demonstrated that large language models can assist with patch generation, it remains unclear whether prompt engineering strategy meaningfully affects patch quality, and no prior study has evaluated explanation quality as a distinct output dimension. Prompt engineering is the practice of crafting and refining prompts to guide AI models towards generating accurate, relevant, and goal-aligned responses. Well-designed prompts clarify context and significantly reduce errors while streamlining workflows and speeding up tasks through smarter automation. A structured prompt consists of 5 essential components: the role, which defines the persona or perspective; the task, which clearly states what the AI needs to do; the instructions, which are the specific guidelines and constraints; the context, which is the background information for accuracy; and the input, which is the core dataset to process. This study conducts a controlled comparison of prompting strategies and models on a single, well-defined task with 2 independent measures of quality. Specifically, few-shot and chain-of-thought prompting strategies were evaluated across GPT-4, Claude Sonnet, and CodeLlama 7b. The models were tasked with generating vulnerability patches for C and C++ samples from the CVE fixes dataset. Each generated response was then evaluated on both patch correctness and structured explanation quality. So let's define few-shot and chain-of-thought prompting. Few-shot prompting gives an AI a few input-output examples to show the pattern, style, or format you want. Chain-of-thought prompting makes the AI write out step-by-step reasoning before giving the final answer. Now let's explore some related studies. Large language models in software security, a survey of vulnerability detection techniques and insights, is a survey of 60 plus LLM-4 vulnerability papers. It found that chain-of-thought prompting and fine-tuning reliability improve vulnerability detection, but unreliable explanations and low patching accuracy remain open problems. These 2 open problems are exactly the gap my research targets. Next, we move on to detection benchmarks on Open Worldwide Application Security Project. Vulnerability detection and monitoring using large language models found that zero-shot prompting on GPT 3.5 reaches 77% detection accuracy on the Open Worldwide Application Security Project. This study was only on 1 model and it was detection only. There was no fixed quality evaluation. Then we have integration of large language models and static analysis for improving the efficacy of security vulnerability detection in source code. This study benchmarks 8 large language models against find sec bugs static application security testing on 2,740 Java Open World Application Security Project cases. The models this study used were CodeLlama, DeepSeek, Gemini, Mistral, 5.3, Qwen, StarCoder, and hybrid large language model plus static application security testing combinations. Next, we have chain-of-thought prompting of large language models for discovering and fixing software vulnerabilities. This study staged a chain-of-thought pipeline that walks a model from identifying to discovering to patching a vulnerability. This study reported a 20% real-world CVE patching accuracy, It also inspired the core methodology my project adopts and extends. Then there is optimizing code vulnerability detection performance of large language models through prompt engineering. This study is a systemic zero-shot versus chain-of-thought comparison for detection. It establishes a clean head-to-head prompting strategy comparison, but only for detection. It reported that 89% F1 score reached by a hybrid chain-of-thought approach on detection. My project ports the same framework used by this study to patching. Finally, we have DiverseVul, a new vulnerable source code dataset for deep learning-based vulnerability detection. This study compares large language models versus graph neural networks. In distribution data, large language models outperform graph neural networks at vulnerability detection. This study reports a 49% to 9% F1 score collapse on unseen projects. Generalization fails, which motivates prompting over fine-tuning. Overall, how my study differs is by introducing newer models and a harder task. My study tests GPT-4 class models and asks the question, is the 20% ceiling a model limit or a fundamental task limit? It also applies the same comparison framework to harder, less studied patching tasks. Additionally, my study adds structured reasoning scoring as a second evaluation dimension and asks whether prompting alone can close the patching gap at zero training cost. My study delivers 3 concrete deliverables. First, a prompt strategy comparison. It identifies which strategy, few-shot, or chain of thought produces the most correct vulnerability patches on real common vulnerabilities and exposures samples. Second, it provides an explanation quality evaluation. It applies a structured reasoning quality framework to score patch explanations, a dimension no prior patching paper has measured. Third, a reproducibility check. It tests whether newer models close the 20% real-world patching gap and characterize which vulnerability types still fail. Overall, it is an empirical benchmark for prompt strategy selection on the vulnerability patching task, which does not currently exist. The dataset I chose to use for my study was CVE Fixes. It is a curated dataset linking real-world common vulnerability and exposures records to their corresponding vulnerability fixing commits, providing paired vulnerable patched code samples for evaluation. It served as sampling base for common weakness enumeration subset. The scope of this study targets 5 high-impact memory, safety, and resource management weaknesses classes selected for the sampling frame. We have CWE 787 out of bounds write, CWE 125 out of bounds read, CWE 476 null pointer dereference, CWE 416 use after free, CWE 190 integer overflow. The evaluation framework consists of 4 dimensions. Grounding. Does the explanation refer to actual variables, line numbers, or code structures present in the snippet? An example of a low score would be, quote, this code has a buffer overflow, end quote, with no reference to which buffer or line. Casual accuracy. Does the explanation correctly identify why the original code was vulnerable? An example of a low score would be if it misidentifies the vulnerability type or describes a different bug than the one present. Fixed justification. Does the explanation connect the specific change made to the specific flaw identified? An example of a low score would be if a patch is correct, but the explanation doesn't say why the change fixes the problem. Coherence. Is the reasoning internally consistent and free of contradictions or hallucinated details? An example of a low score would be if the generated patch references a function or check that doesn't exist in the code. Each dimension is rated on a scale Each dimension is rated on a 1 to 4 scale, then combined into a single composite explanation quality score per sample, 1 being poor, 2 being weak, 3 being adequate, and 4 being strong. The scores across grounding, causal accuracy, fixed justification, and coherence are summed and averaged into one composite per sample, enabling direct comparison across few-shot and chain-of-thought prompting. By using a simple sorting script based on vulnerability ID, the approximate vulnerable functions returned by the CVE fixes query by weakness class is shown on this slide. As part of my methodology, I primarily use 6 Python scripts that query, filter, sample, pilot, and validate the evaluation set end to end. Inspect DB explores the CVE fixes database schema and available records. Run filter filters the C and C++ functions in the 5 target CWEs. Sampling script draws the stratified 200 sample set, 40 per CWE. Full few shot pool reserves 5 CWE as the few shot example pool. Pilot set builds a small pilot subset for an initial end-to-end trial run. Check set validates the final set, balance, no leakage between few shot and evaluation splits. I queried CVE fixes, then applied stratified sampling to build a balanced evaluation-ready subset across 5 target CWEs. From the original 4,000 pairs, 200 samples were drawn by stratified sampling, 40 per CWE. Then 4 per CWE were reserved as few-shot examples for the prompts. Finally, 2 per CWE were kept for the pilot set, outside the evaluation set, and few-shot pool. Improvements were made to the initial sampling script. Some of these changes include rewriting the script to improve performance, taking into account non-deterministic limit 1 pairing, and including multi-CWE tag handling. These changes matter because a benchmark's validity depends entirely on correct ground truth. These bugs could mismatch or duplicate pairs with no visible errors. So, to address these issues, I built diagnose pairing script to quantify the problem first. 336 samples tagged under more than 1 CWE and 25 methods with ambiguous before and after matches. I made the decision to drop both categories entirely rather than arbitrarily pick a CWE or accept a non-deterministic match. This was the cleanest, most defensible choice given the eligible pool was large enough to absorb the loss. Then, I replaced the n+1 loop with a single batch query, making ambiguity visible in the merge logic instead of hidden inside a per row database call. This reduced the eligible 3,000 rows to around 2,000 clean rows to 200 stratified samples. I then rebuilt the few-shot example pipeline to generate candidate pools for handpicking few-shot examples, applying the same dedupe ambiguity fixes as the evaluation set. It is important to note that no evaluation set is reused as the few-shot example. It is important to note that no evaluation set method is reused as a few-shot example, as few-shot examples function as the model's training data. For this task, leakage here would mean the model is its own answers. I then rebuilt the few-shot example pipeline to generate candidate pools for handpicking few-shot examples, applying the same I then rebuilt the few-shot example pipeline to generate candidate pools for hand-picking few-shot examples, applying the same dedupe/ambiguity fixes as the evaluation set. It is important to note that no evaluation set method is reused as a few-shot example, as few-shot examples function as the model's training data for this task. Leakage here would mean showing the model its own answers. I then built Select Few Shot, which is an interactive tool to review candidates against a 5-point checklist. Those being self-contained, meaning no signature changes, CWE mechanism, visible in vulnerable code. Fix is minimal and obviously correct. The code length is 100 to 1,500 characters. Diverse fix patterns across picks. Using these heuristics, I rejected several real CVE fixes because the protective logic lived in unseen helper functions or the signature changed. These would make it impossible to write an honest explanation from the shown code alone. Additionally, we discovered some CVEs are fixed as part of large, unrelated commits. For example, a TensorFlow CVE bundled with a mass namespace rename, an SNMP library CVE bundled with an unrelated multifunction API refactor. So I cross-checked findings against real GitHub commits and security advisory advisories before excluding anything, confirmed via external sources rather than assuming. This systemic risk was important to discover as CVE fixes labels every method touched in a fix commit as part of the fix, with no way to distinguish the actual patch from incidental changes, meaning it's structural dataset limitation, not a one-off error. So, to build systematic detection across the dataset, I created 3 scripts. Scan trivial diffs, tokenizes before and after code, and flags rows where very few tokens change relative to function size. This catches renames, whitespace only differences, and comment typos masquerading as fixes. CVE sweep groups flagged rows by CVE to detect repeat offender mega commit, CVE contributing to disproportionate noise. Pool by CVE pulls every row under a specific CVE for full manual verification once a suspect CVE is identified. The effects for using a general token identity filter is that any row where before and after code tokenizes identically is dropped automatically. This closes the entire noise class in one step. However, by going through such rigorous filtering, it is important to prevent diversity collapse. So I built CVE concentration report to check whether any single CVE was dominating a 40 sample CWE stratum. What I found was that 35% of CWE 190 stratum was one CVE. The fix was to insert a cap of 3 samples per CVE per stratum. This was chosen after comparing cap 1, 2, and 3 against actual data. A stricter cap would have forced unnecessary rework in the strata that were never actually concentrated. One important aspect of this study to communicate upfront is that it is currently in its active experimental phase. The pipeline infrastructure is complete, the dataset construction, quality filtering, few-shot creation, prompt design, and experiment orchestration are all done. Model output generation is underway, 1,200 outputs which is 200 samples by 3 models and 2 prompt strategies. The evaluation framework requires manual scoring of all 1,200 model outputs, 200 test samples evaluated across 3 models, and 2 prompt strategies. Using a 4-dimension explanation quality rubric measuring grounding, causal accuracy, fixed justification, and coherence, each scored on a 1 to 4 scale along a 3-tier patch correctness judgment. This manual scoring process, which also includes a structured inter-rater reliability check using a quadratic weighted Cohen's kappa on 20% of outputs, represents the most time-intensive phase of the research and is estimated to require 2 to 3 weeks of sustained full-time effort to complete with the rigor the methodology demands. Rather than rushing this process and compromising the validity of results, the decision was made to prioritize scoring quality over speed. Final quantitative results will be available once the manual evaluation phase concludes. Here are some of my sources.